Hello everyone. I'm sure that you have gone through the two presentations that we have given on design of IC engine components, in which we have learned about design of cylinders and pistons for an IC engine. In continuation, today we intend to learn about design of connecting rod. The outcome of this presentation will be students shall be able to understand the functions of connecting rod, which is a very important part of an IC engine. Students will be able to know what are likely materials that can be used for connecting rod. Then students will be able to know the design portion, that is determining cross section of the connecting rod, determining length and diameter of small end bearing, length and diameter of big end bearing, diameter of big end bolts, thickness of big end cap, and other associated parameters. You must be feeling that these are very new terms: small end bearing, big end bolts, big end cap. But be patient. I'm sure that when we'll end this presentation, you will be familiar with these terms. Let's start. The functions that a connecting rod performs is shown in this slide. This GIF image shows that connecting rod is used to transmit push and pull forces from the piston pin to the crank pin. Piston pin is that portion which connects connecting rod from the piston, and crank pin is that portion which connects crankshafts to the connecting rod. So we can say that connecting rod acts as a link between piston and crankshaft. Further, piston always has reciprocating motion in the cylinder, whereas crankshaft has rotary motion. So, design of connecting rod is unique in the sense that its one end is having pure translation motion and one end is having pure rotational motion. Another function of connecting rod is it also transfers lubricating oil from the crank pin to the piston pin and provides a splash of oil to the piston assembly. As it is clear from this diagram, the oil is being filled in the crankcase, and connecting rod has a mechanism that it takes oil from the crankcase and transfers it to the piston for proper lubrication. This is called as splash lubrication and used in some diesel engines and petrol engines. Now, since the functions that a connecting rod is supposed to be performed are unique, so its design is also a bit different. As you can see, this is one assembled connecting rod. It has mainly two parts. This is connecting rod, this is its small end, this is its big end, and this is big end cap, which is being fastened to this big end by means of two bolts. The whole of the connecting rod is forged into one piece, and the bearing cap is cut off, phased, and bolted for final machining of the big end. The small end of the rod is generally made as a solid eye and then machined. This slide shows the assembly of piston, connecting rod, big end cap and bolts, and gudgeon pin. This is another view of the same assembly. Now, to be able to design a connecting rod, we must know that what are the forces that are being acted upon a connecting rod. Connecting rod is one of the most heavily stressed part of an IC engine. It is subjected to the force of gas pressure, which is being applied over here, and inertia forces of the reciprocating parts, Pi. These are given by these formulas. Force due to gas pressure is pi by 4 d square into P max, where P max is the maximum pressure, which is generally 10 times indicated mean effective pressure, and d is diameter of cylinder. This is force, maximum gas force, and inertia forces are given by this very well known formula, mr omega square r cos theta plus cos 2 theta over n1. Mr is mass of reciprocating parts, omega is angular velocity, r is crank radius, theta is angle between connecting rod and crank, and n1 is ratio of connecting rod length and crank radius. So these two forces will play a vital role in designing of connecting rod. Let us talk a bit about length of connecting rod. When connecting rod is short as compared to crank radius, it has greater angular swing, resulting in greater side thrust on piston. This means that length of connecting rod has useful implications on the forces that are about to be encountered. So, in high-speed engines, the ratio of length of connecting rod to crank radius is taken as 4 or less, whereas in low-speed engines, this ratio varies from 4 to 5 because the length is going to be an important parameter as it decides the magnitude of inertia forces. Let us talk a bit about the materials that are likely to be used for connecting rod. Connecting rod of industrial engines are made up of medium carbon steel having 0.35 to 0.45% of carbon, whereas connecting rod of automobile engines are made up of alloy steels. Aluminum alloys can also be used as they are light and they can absorb impact loads. In some cases, titanium is used for high performance engines. Since length of connecting rod is substantial as compared to the crank radius, so this L by R ratio is important. So mostly connecting rod is being designed treating it as a column or strut. Now, if we design it treating the same as column or strut, we need to take buckling into consideration. Now, buckling can occur in two planes. One is plane of motion, which is being denoted by this along x-axis, and along a plane that is perpendicular to the plane of motion, shown in this diagram. These two cases will help us to decide the end conditions because here ends are hinged whereas here ends are fixed. We know from Euler's formula PCR, that is crippling load, is given by n pi square EA over L by K square, where n is end fixity coefficient, which is 1 when both ends hinged and 4 when both ends fixed. So, if we want to design connecting rod treating it as a column, we need to be sure that our rod should be equally strong in buckling about x-axis as well as y-axis. Why we are doing this? We are doing this because prior to design we want to fix what is optimal cross section of a connecting rod, and this analysis will help us in deciding the cross section of connecting rod. If we put the same PCR formula, n equals to 1 for XX buckling and n equals to 4 for YY buckling, substituting k square equals to I by A, PCR comes out to be n pi square EI over L square. Now, assuming that our rod is equally strong in buckling about both the axes, so crippling load for y-axis and x-axis should be same. So here, keeping all other parameters as constant, it is 4Iyy should be equal to 1 times Ixx, or Ixx should be 4 times Iyy. Now this is necessary condition for any connecting rod to be equally strong in buckling about x-axis and y-axis. If we see this section, this is an I section. Besides having other advantages like it is light, it has more strength. The other advantage of I section is it its I-axis is 3.2 times Iyy with these dimensions, like this height is 5t, this is 4t, and all the webs and flanges are equal to t. So I section is the only section which is having this relation which is in close proximity to the required relation. I repeat, I section is the only section which gives value of Ixx equals to 3.2 times Iyy, and which is closest to what is required for a connecting rod to be equally strong in buckling about XX and YY axis. On the other hand, circular cross section is unnecessarily strong for buckling about Y axis. So here we have freezed that for a connecting rod to be equally strong in buckling about XX and YY axis, the most appropriate cross section is I section with these dimensions. Now, our job is just to find this T so that we can suggest what will be the cross section of connecting rod. Let us talk about design of connecting rod. It implies that while we are designing a connecting rod, what we are supposed to find. So our job is to find what will be cross section of the rod. As we have seen that a connecting rod is having one small end, one big end. So we need to find what will be the length and diameter of small end bearing, what will be length and diameter of big end bearing. And since big end bearing will have big end cap which is fastened by means of bolts, so we need to find dimensions of big end cap and spoles also. And then in the end we need to check for whipping action. What is this whipping action? We'll discuss in the coming slides. So now we are in a position to find what will be the procedure to find cross section of the connecting rod. As you can see, this P force is the gas force which is coming on the rod, which is coming on the piston, and this is the force which is coming on the connecting rod. This angle is phi. This is the force diagram. Force acting on connecting rod PC from this triangle we can find it is P upon cos of phi. This force is maximum when phi is 3.3 degrees. Since cos phi is equal to cos 3.3 equals to 0.99, which is very close to 1, so we can assume PC equals to P. So we'll assume that the force that is coming on the cutting rod is equal to the gas force. So Pca is pi by 4 d square into Pmax. Now, since we are designing it, treating it as a column, we'll use the Rankine formula, which is PCR sigma C A 1 plus A L upon Kxx whole square. Here sigma C is compressive stress, A is area of cross section, A is a constant that depends on the material of the cutting rod. For steel, its value is 1 upon 7500. L is length and Kxx is radius of gyration. Now, since we have decided the cross section beforehand, we just need to put the values of A. For this cross section, the value of area is 11t square. Kxx is known to us for this cross section in terms of t, that is 1.78 times t. Since we have found the load which is coming on the cutting rod, so we'll find the crippling load by multiplying the load on cutting rod by some factor of safety. It is usually 5 to 6 times PC. So PCR will be 5 to 6 times PC, where 5 to 6 is a factor of safety. That means that suppose load on rod is coming out to be 10,000 newtons, then the rod will be designed for 50,000 newton. 50,000 newton will be treated as crippling load. So if we put all these values, PCR is 5 to 6 times P, sigma C is the compressive stress for the material of cutting rod. For steel, its value is 330 megapascal. A is 11t square and Kxx is 1.78 t. A is also given. In this equation, the only unknown left is t. So putting all the values, we can find what will be t. Now, as we see, this height of cutting rod is 5t. It is height in middle because small end will have lesser height and big end will have more height. Whereas width, which is 4t, it is kept constant throughout. So height at the small end will be 0.75 h to 0.9 h, and at the big end it will be 1.1 h to 1.25 h. So this slide will give us the dimensions of cutting rod with the condition that we have used I section as the most appropriate section. Next comes small end bearing, also called as piston pin bearing, because at this end piston is being attached to the cutting rod by means of piston pin or gudgeon pin. The small end bearing is usually a phosphor bronze bush of 3 mm thickness, shown over here. It is solid one-piece bushing made by casting and then finished by grinding and reaming operation. Our job is to find the length of this bearing and diameter of this bearing. The force acting on the piston pin is given by same force PC pi 4 d square to P max. Also, we know that PC is dPLP, which is projected area, and PVP is maximum pressure on bearing. If its value is not given, it is assumed as 10 to 12.5 megapascal. And when we have designed the bearings, we found that this ratio, L by D ratio, is given for most of the cases. So for small end bearing, this L by D ratio is 1.5 to 2. So PC is already known to us. PP we can put if we know the ratio. So this equation will be having only one unknown, either LP or DP. We can find, and putting the same in this ratio, we can find the other. So it is possible for us to, by using these formulas, to find length and diameter of small end bearing. This is being used for designing big end bearings also. The big end bearing is a line bearing that is split into two halves. It consists of steel backing with a thin lining of bearing material like babbitt. It is seen over here. So we need to find this LC and DC. The force acting on the crank pin is given by the same formula, and again PC is DCLC into PBC. At the big end, this allowable bearing pressure is 5 to 10 megapascal, and for the big end bearing, this ratio is 1.25 to 1.5. I must tell you one thing, that we need not remember these formulas, these values. These values will be available in the data book, any standard data book that will be provided to us. We have designed the small end bearing, the big end bearing, the cross section of rod. What else? Big end cap and bolts. Now, the maximum force acting on the cap and two bolts consists only of inertia force at the top dead center on the exhaust stroke, and is given by mr omega square r cos theta plus cos 2 theta over n1. We have seen this formula earlier also, where mr is mass of reciprocating parts. It consists of the whole mass of piston assembly plus 1 by 3 of mass of connecting rod. We know that the value of inertia force will be maximum for theta equals to 0. So Pi maximum is mr omega square r 1 plus 1 upon n1, where n1 is ratio of length of rod to the crank radius. This Pi max will be acted over here. So by visualization we can be sure that this big end cap will be designed considering it as a beam with central load equal to Pi max, and this Pi max will tend to induce tensile stress in these bolts. So with these criteria we will try to design cap and bolts. The bolts are subjected to tensile forces. Since there are two bolts, each will share the maximum inertia force equally. That is, Pi max is equal to, this is resisting force, two bolts, the area of one bolt is pi dc square by 4, and the permissible stress for the bolt material. Dc is core diameter. If we, in this equation, the only unknown left is dc. So we can find dc, and using the relation dc is 0.8 times nominal diameter, we can find diameter and bolts. What else? The dimensions of big end cap. The big end cap is treated as a beam that is freely supported at the bolt centers and loaded in a manner intermediate between uniformly distributed and centrally concentrated load, where bending moment is given by this equation. Maximum bending moment is Pi max into L by 6, where L is the distance between the center line of two bolts. L, we can find L by, L is DC, which is diameter of crank pin, plus twice thickness of bush. Bush will be, thickness will be somewhere over here, plus diameter of bolt plus clearance, which is usually 3 mm. So if we put this value over here, Pi max is known to us. If we put value of L over here, the only unknown left is TC. So using the famous formula m by I equals to sigma by y, and treating this to be under bending, we can find I as BC TC cube upon 12, where BC is nothing but width of this cap, which is equal to length of big end bearing that we have already found. So putting the value of MB over here, Y as TC by 2 and I as this, it will have only one unknown, and that is TC, thickness of cap. We can found thickness of cap using this formula. So up till now we have found the cross section of rod, length and diameter of small end bearing, length and diameter of big end bearing, thickness of big end cap, and diameter of big end bolts. There is one more concept left, that is concept of whipping stress or whipping action. What happens? A small end of fritting rod is subjected to pure translation motion, whereas big end is subjected to pure rotary motion. What about the points that are in between small end and big end? The intermediate points on the rod will move in elliptical orbits, and the lateral oscillations of the rod induces inertia forces that act all along the cutting rod, causing it to bend. This action is called as whipping action, and the bending stress thus induced is called as whipping stress. So since we have found all the dimensions, our job is to just determine the whipping stress and check whether the stress is within the permissible limits or not. If yes, it's fine for us. If it is not, then we might need to change the dimensions of rod so that the whipping stress is within the permissible limits. How will we do this? Let's see. This slide shows the magnitude of the forces on the big end, small end, and the points in between. This is drawn from Klein's construction diagram of acceleration. We can see over here, this is the force at point C, and this is force at some intermediate point. And for this type of loading, the maximum bending moment occurs at a distance of L by root 3 from the piston pin bearing. The variation of the forces on the rod is linear and is like a simply supported beam of variable loading. If we know the concepts of mechanics of solids, we can recall the formula for the same, and in such a case bending moment is found to be m1 omega square r into L square over 9 root 3, where m1 is mass of rod per unit length, which is area into density. Area is same 11t square for the standard I cross section we have chosen, and density is the density of material of cutting rod. So with this we found the whipping stress by this formula sigma b as mb into y ixx, where ixx is the same for the standard cross section and y as 5t by 2. So what will we do? We'll, because we know everything over here, we have already found what is t, and we have already found the other parameters also. So we just need to determine the sigma b over here, and we need to check whether the sigma b is less than or equal to sigma permissible for the material of the connecting rod. So in this small presentation, we learned about the functions of connecting rod and various other concepts of connecting rod, and also learned about the design of connecting rod, that is how its cross section is decided, how diameter and length of small and big end bearings are checked and decided, and how we'll find the dimensions of big end cap and bowls. And in the end, we also learned about the whipping action and how to check a connecting rod for the whipping stress. We'll solve some numericals also, some unsolved numericals also on this connecting rod design, so that the concepts that we have learned will be more clear. I hope that you have enjoyed this presentation. I thank you all for your patient hearing. I'll be back with more topics on design of machine elements. Thank you so much.